All right, y'all. So today we are going to be going through this Unit 1 set of notes over atomic structure and mass spectroscopy. So in this is stuff that y'all have been learning throughout your careers in high school and before in middle school. So just throughout schooling in general. It's going to be kind of the building blocks of chemistry, kind of the things that put everything together. And in this, one of the central tenets, one of the central things that we kind of focus on is the law of conservation of mass. And what that says is that mass is neither created or destroyed in a chemical reaction, but it can change form. Okay, so I could rearrange the way that the atoms are, but if I start with 5 carbon atoms as a reactant, I'm going to end with 5 carbon atoms in the products. Okay, so everything should be the same when you're done. Okay, you can rearrange them. So I could start with 1 carbon and 2 oxygen as a reactant, and I could produce a carbon dioxide as a product. But again, I've got 1 carbon and 2 oxygen on the reactant side, 1 carbon and 2 oxygen on the product side. Okay, all right. So with that being said, when we're talking about this law of conservation of mass, a lot of times what comes up are your protons, neutrons, and electrons. Because in the grand scheme of things, protons, neutrons, and electrons are also not going to change because we get our mass from our protons plus our neutrons. Okay? So, for our subatomic particles, protons, neutrons, and electrons, these would be what we have. So I have, again, protons, neutrons, and electrons. And they actually do have a mass. Even electrons do. Okay? But a lot of times the mass is not very much. Specifically with an electron, it's extremely small. Okay? The big example that I give is if I've got something like a pencil. Okay? And let's say a proton is the mass of a quote-unquote pencil. If I add an electron to that, it's kind of like adding a grain of sand to the side of that pencil. It's not really going to change the mass. It'd probably be unnoticed entirely. Okay? And so because of that, electrons, a lot of times we say that they have a mass of 0. Okay? Protons and neutrons technically have a mass as well. And while it's technically not exactly the same, it is very close. Now, again, these numbers are extremely small masses. Okay, extremely small masses. And so because of that, it doesn't really make sense for us to work with their exact mass. Instead, we give them what's called a relative mass. That's where this comes in. That's where the mass that you think of for a proton and a neutron as 1 comes from. Okay, so we work with a relative mass instead. So if you notice, technically, your protons and your neutrons' masses aren't the same, but they're so close that the difference is negligible, and so we don't even worry about it. And a lot of times we'll just say that protons have a mass of 1, neutrons have a mass of 1, and then electrons, if you notice, it's an extremely small number, so we say it's got a mass of 0. Okay? Next thing is your charge. Your charge is, again, relative, kind of like your masses. Technically, there's a number that's involved. That's what we see right here. Okay, but again, that number is a strange number to work with, so we give it a relative number. Protons are positive, electrons are negative, neutrons are neutral. Okay? All right, I'm going to fly through the rest of this next section right here because, again, this is something that I'm hoping that a lot of y'all already know. So, first off, in the center of the atom, we've got the nucleus. The nucleus contains the protons and the neutrons. It is extremely small. Okay, the majority of the atom is actually just open space. Okay, next we've got electrons. Electrons determine the chemical behavior, so they're going to determine what that chemical reacts with. Okay, it's all based off of your electrons. The chemical behavior, be it toxic, non-toxic, be it reactive, non-reactive, whatever it is, that's based off of your electrons. Okay? Next, if I've got an atom of some type, let's say carbon. Carbon always has the same number of protons. Okay? Carbon always has 6 protons. Okay, and with there always being 6 protons, how do we sometimes end up with different masses? Well, we end up with different masses because there's things called isotopes. Okay, and isotopes come about because each atom could have a different number of neutrons. Okay, and so with that being said, we have to talk about the isotopes because it's going to affect our mass number. Okay, and mass number is just your protons plus your neutrons. Okay, so an isotope is an atom that has the same number of protons, but it does have different numbers of neutrons. Okay. Next, I've got my atomic number. That equals my number of protons. I've got my mass number, which is, again, the protons plus the neutrons. And then when I'm writing it, I could write it like this, or I could write it like this. So I could have nuclear symbol notation / isotopic notation, or I could have mass number notation, which is just going to tell me my mass. Okay, so it'll tell me the element and the mass. Isotopic notation is going to tell me my mass, the charge, the atomic number, all those things are going to be in there. Okay? All right. So we also have atoms that can form a charge. And again, remember, charge is how we determine the chemical behavior that a thing has. So remember, your number of protons will equal your number of electrons if the atom is neutral. Okay? If the atom is not neutral, then you will have gained or lost electrons throughout whatever has occurred. Okay? Be it a reaction with something or because of energy being added or whatever it is, you will have gained or lost it. Okay? So for this next section, what I want y'all to do is I actually want y'all to take a little bit of time in looking at carbon 12 and carbon 14. I want you to represent protons, neutrons, and electrons. So make a drawing. Protons are squares, neutrons are triangles, and electrons will be circles. And I want y'all to pause the video here, and then I want you to actually go in and draw out the protons, neutrons, and electrons for carbon 12 and carbon 14. Okay, so pause your video and go ahead and do that. Okay, hopefully y'all paused the video. Now you have started the video, and let's see what we have. Okay, so this is what you should have ended up, or something similar, for carbon 12. So you should have had 6 protons, 6 neutrons, and then your 6 electrons would have been orbiting around those protons and neutrons. Okay, next we've got our carbon 14. Okay, and this is what you should have ended up with for carbon 14, where you've got 6 protons still, because again, it's still carbon, but now you've got 8 neutrons. Okay, and then for our electrons, they should have stayed the same because our charge is neutral. Okay, so that's what we got right there. Now, if our charge is not neutral, we form what's called an ion. And again, ions form when you have either gained or lost electrons. Okay, cations are positive. Anions are negative. I have always remembered cations as positive because I think that looks like a plus sign, which is positive. You could also remember it as cats have paws. Okay, so cations are positive. Okay, for anions are negative. I've always remembered this as a negative ion. So A-N-I-O-N, a negative ion. You can also remember it as anions, looks like onions, and onions make you cry, which is a lot of times considered a negative emotion. Yes, you can have a good cry and it makes you feel better. So it's not always a negative thing, but okay. So anions are negative, cations are positive. We get cations when an atom loses an electron, one or more, and then anions happen because an atom gains an electron, one or more. Okay, so cations lose electrons, anions gain electrons. Okay, now when that happens, we actually form what's called electrostatic or Coulombic attraction. Okay, and that's between oppositely charged ions. Okay, and so because of that, because of this opposite charge, they're going to start to attract each other, which is how we get what's called an ionic bond. We'll go a little bit more into that later on, probably next week. But I did want to bring that up. When you've got those ions that form, we can start to form these electrostatic or Coulombic attractions between atoms. Okay? Now, what I want y'all to do is to, again, pause the video, go through and identify the number of electrons, protons, and neutrons in each of these substances. All right? Again, pause your video, work through them, then come back after you've paused it and work through those problems, and I'll quickly pull up what the answers would be. Okay? All right, so hopefully y'all paused, but here are your answers for that set of problems. Okay, so you can pause your video if you want to double check and look through all those. You got 8, 7, 8 for the first one for protons, neutrons, electrons, then 8, 7, 10, then 26, 29, 23, 10, 10, 10, 17, 18, 18, and 17, 18, 17. Okay, so that would be all of those so that you could identify your number of electrons, protons, and neutrons that each of these substances have. Okay? All right, so now we've talked a little bit about the atomic structure. So basics of the atomic structure. What's a proton? What's a neutron? What's an electron? What are their relative masses? What are their relative charges? All that stuff has kind of been gone over. So now let's look at where we get the average atomic mass, that mass that you can find on the periodic table. So in the perfect world, everything would have the exact same mass and everything would be perfectly in order and everything is great. But that's not how the real world is. The real world is chaos, right? So in that real world, we have different numbers of protons and neutrons, and we get those, again, isotopes, okay? And isotopes are all over the place. For example, oxygen technically has 16 different isotopes that have been found. Now, some of those are man-made, but there are 16 different isotopes that have been found. Now, in those 16, only 3 of them are actually stable and very common, and we find them pretty often in the natural world. But there are a lot of isotopes that have been found for oxygen. Okay, well, if you look at your periodic table, oxygen has a mass of 16. So why don't we find that there are only oxygen with 8 protons and 8 neutrons? Well, it's because, again, in the real world, everything is not perfect. Okay, so because of that, what we have to do is find the average mass. Now, that comes from what we call a weighted average. Okay, and here's how we solve for a weighted average. So we take the isotope that we've got and we multiply it by its abundance. Okay, and the abundance is going to be what percentage I have of that substance. Okay, be it 70, 80, 92%, whatever it is by its percentage. Okay, then you do plus isotope B times its abundance, then plus isotope C times its abundance, and that can go on until you run out of isotopes. Okay. Now, again, you repeat that as many times as you need to find what your average atomic mass would be. Okay. Now, what is abundance? Again, it is the percentage that you find of that substance. Okay. So it's the number of atoms of a given isotope divided by the total number of atoms that you're working with. Okay. So the total of all the isotopes that you have. It's the same thing as anytime you find a percentage, part over whole times 100. Okay, so that's how we found the percent abundance. Okay, so here is our first question here. So it says calculate the average atomic mass of magnesium, which has 3 isotopes. Okay, well, here are our isotopes: magnesium 24, magnesium 25, and magnesium 26. Okay, again, these would be our mass numbers. Okay, so these right here are our mass numbers. And again, mass number comes from adding your protons and your neutrons together. Okay. Now with our mass numbers, we also have percentages, that percent abundance. Okay. And that percentage again came from our part divided by our whole. All right. Okay. So again, that's our mass number. Now let's look at our percent abundances. So for our percent abundances, again, that came from our finding the number of the atom divided by the total number of atoms that we've got. So part over whole. These percentages, I don't like to work with percentages. And the reason I don't is because a lot of times I will forget to actually go in and add that percentage sign at the end. So I do suggest that you go in and change these into decimals. So to change that, take that decimal, move it over twice. So we get 0.7899. We're going to do that with all three of those. So 0.100, 0, and 0.1101. Okay, so now we've got our abundances, and they've actually been converted into decimals to make them a little bit easier to work with when we're plugging them in to solve this problem. Okay, now looking back to our average atomic mass formula, it's isotope A times its abundance plus isotope B times its abundance plus C times its abundance, and so on. So I have isotope A, which is magnesium 24, times its abundance. But here's the thing, y'all. Right here, they actually gave us the actual atomic mass. So yes, magnesium 24 theoretically has 12 protons, 12 neutrons, and so we've got the mass to equal 24, but again, technically, it's a little bit different. So sometimes they'll give you the actual atomic mass. And so that's what we see right here with the 23.98504, okay, right here, okay. If they give you your actual mass, that's the one that you should use, okay. So again, if they give you your actual mass, it's the one that you should use. Okay, so I take my abundance and I multiply it by the mass. So 0.7899 times 23.98504, and that's going to give me 18.95. Okay, and we're going to do that same thing with all three of these. So 0.1000 times 24.98584, which will give me 2.499. And then lastly, the 0.1101 times 25.9825. That gives us 2.861. Okay, so that's multiplying, but now we need to go back and add all of those together. Okay, and that's going to give me 24.31. So my average atomic mass is 24.31 AMU. Okay, atomic mass units. Okay. All right, next one. This one's a little bit more tricky because this one, they're not going to give you your percentages. You actually have to solve for them. So it says calculate the percent abundance of chlorine 35 and chlorine 37 if the average atomic mass of chlorine is 35.453 AMU. Again, this is going to require some algebra knowledge, okay? It's basically a system of equations. So here, I'm told that I have chlorine 35. So 35 times its percentage. Well, I don't know its percentage. So we're going to put X. Okay? Plus chlorine 37 times its percentage. Again, I don't know that. So Y equals 35.45. Okay, so how do I solve this? Well, one thing I know is that in the end, my percentages always add up to 100, right? So if I have percentage for chlorine 35 plus percentage for chlorine 37, that's going to equal 100%. Okay, so X plus Y is going to equal 1.00 if we convert that out of percentages. Okay. I personally like when I'm solving a problem, so this problem right here, I personally like to solve for X. So that's what I'm going to do. I'm going to replace my Y with an X. So Y equals 1.00 minus X. Now I can replace that Y with X. So how do I do that? 35 times X plus 37 times. Now I'm replacing my Y with what Y equals over here. So Y equals 1.00 minus X. And then that's going to equal our 35.453. Okay. Now, I need to go back in and start solving this. So I have 35x plus 37, because that was 37 times 1, and then plus 37x, which is 37 times x. Now, it wouldn't be plus, it'd actually be minus, because we subtracted that x there. And that's going to equal 35.453. Again, we're solving for x. So 35x minus 37x equals 35.453 minus 37. So negative 2x equals negative 1.547. Divide both sides by that negative 2, and you're going to get 0.7735. Okay, so there's our decimal, but they've asked me for my abundance, so let's convert that back into that percentage, which is 77.35%. Okay, so 77.35% of that is chlorine 35. Okay, well, I also need to find out about chlorine 37. Well, how would I do that? Well, I know X plus Y equaled 100. So my percentage of chlorine 35 plus my percentage of chlorine 37 is going to equal 100. So I can do 100 minus 77.35, and I'm going to get 22.65. So my percentage of chlorine 37 is 22.65%. So those would be my two percentages. Okay? All right. So that should have all been a little bit of review. Now, you might not have done something like this percent abundance here in the past, but hopefully you found it fairly easy. And again, ask any questions if you've got any questions, either next class or shoot us an email and we'll answer it for you. So moving on. So we do need to know what average atomic mass is and how to find those weighted averages for mass spectroscopy. Okay. So mass spectroscopy is actually how we figure out how many of each of these, or what the average atomic mass is, and how many of each individual isotope we have. Okay? So here's what I want you to do. Before we actually start on this, I want you to come down, read through all of these. Read through them all, and I want you to assign them a letter, be it A or B or C or D or E, F, G, and lastly H. So I want you to try to figure out what's going on in each of those things in a mass spectrometer. Okay? So pause your video, go through, label each one of those as A through G, and then we will go over that after y'all have done that. Okay, so pause your video and do that. Okay, so let's go over that. So first off, looking at A, what do we see here? Well, we see that there is fire, right? So that fire tells me that they're actually heating up the substance, okay? So heating up the substance, that is right here. It's a sample of the element is being heated to vaporize it. So we're trying to convert it into its individual gaseous atoms, okay? Now, once we've done that, what's going on here in B? Well, B is right here. Its high voltage electric current passes through those gaseous atoms. Okay, so that's what we see with this lightning bolt right here. It's that electric current passing through them. Now, when it does that, what we're going to see is that it's going to actually knock off electrons and change them into positively charged cations. Okay, so those electrons are getting knocked off. And if you look very closely, you'll see that each one of these has a little positive symbol inside of it. Okay, so we've knocked off electrons, and we've made those positively charged now. Okay. Next, all those all those positively charged atoms are going to be accelerated through this negatively charged ring. Okay, so we're going to take those those cations, and we're going to push them through, and they're going to run through these rings of negatively charged rings, and it's going to accelerate them. It's going to make them move faster. Okay. So it's going to push those cations through. Okay. Next, we're going to go right here, where the beam of those ions is actually going to pass through two rotating disks with staggered slits in them. Okay, and what that's actually going to do is it's going to ensure that everything is going at the velocity that it should be going at. Okay, so if it's going too slow or too fast, it's going to make sure that it's only going through at the right speed. Okay, so it's going to be coming through here. If it's going too fast, it'll hit before. If it's going too slow, it'll hit after. But if it's going the right speed, it's going to pass straight on through. Okay, all right, now, next thing we are going to do is that beam of cations is passed through two oppositely charged plates. So if you look at this plate, again, we got positives on this bottom plate and negatives on this top plate. Okay? Well, what happens if you've got a positively charged thing and it comes near another positively charged thing? They repel. Okay? What happens if you have a positively charged thing and it comes near a negatively charged thing? It's attracted. So we've got these two plates. One's going to push them away and the other one's going to pull it towards. Okay, and that's what happens there with those two plates. Now, why do we see some of them coming up short, some of them going in the middle, and then some of them going here at the end? Well, we've already talked about isotopes, right? So isotopes have different masses. So the more mass they have, the more it's going to take to pull them up into that negatively charged plate. So it's going to take a little bit longer for that to happen. Okay? And so G is going to be those cations are deflected towards that negatively charged plate, and the lighter ones are going to be deflected quickly. The heavier ones are going to take a little bit more, and so they'll go further to the end of that plate. Okay? So then how do we get this? Okay? Well, the mass spectrometer, what it's going to do is then take that, it's going to analyze the plate, and it's going to see how many times that plate was hit by those cations. Okay? The more that plate is hit, it will add up to these numbers that you see right here. Okay? So in this case, the substances with a mass number of 67, those isotopes with a mass number of 67, hit the plate 30 times. Mass number of 70 hit the plate about 57 times. And then with a mass number of 72, hit the plate about 12 to 15 times. Okay? So that's how a spectrometer works. Okay? So, according to the mass spectrum shown above, what are the three isotopes of X and what are their corresponding percent abundances. Okay. So I had the three isotopes are 67, 70, and 72. So it's element X with a mass number of 67, element X with the mass number of 70, and element X with the mass number of 72. Okay? Now, how often do they occur? Well, here I've got 30, here I've got 57, and here we said between 12 and 15, so let's say 13. We add those up, well, we're going to end up with 100, right? So our percentage is going to equal 100. So then 30% is 67, 57% is 70, and 13% is 72. Okay, so now let's analyze a couple of these. So after they run them through the mass spectrometers, this is what we get. We get these little tables like this, okay? Now, sometimes they'll give you what the mass spectrometer would actually spit out, and other times they will give you a bar graph like this. They're basically the same thing. Just make sure you're reading the numbers that they give, okay? So here we would have a mass number of 20. We would find this many. Here, a mass number of 21, we'd find that many. And here, mass number of 22, we'd find that many. Okay? So here's a sample problem. So when a sample of natural copper is vaporized and injected into a mass spectrometer, the results shown in the figure are obtained. Use these data to collect the average mass of natural copper. The mass values for copper 63 and copper 65 are 62.93 AMU and 64.93 AMU, respectively. Okay. Well, here, first off, one thing that we can note is that these two are going to add up to 100. If they don't add up to 100, then you need to make sure to go back to that percent abundance and make sure you're double checking how to do that. Part over whole times 100. Okay. So these add up to 100%. Just makes things a little bit easier. So I have copper 63. Now, can I write 63? No. And the reason I can't is because they actually gave me the actual mass. Okay. So if they give you your atomic mass, you need to make sure to use the actual number they give you, not the mass number. Okay. So I have 62.93 times my percent abundance, which they told me was 69.09. Okay, well, again, we shouldn't be working with those percentages, so I should have 0.6909. That plus the next one. So our AMU is 64.93 times your percent abundance, which was 0.391. And then that will give me my mass, average atomic mass. Okay, the average mass of this copper. So we plug that into our calculator. We're going to end up with, for this one, 43.48 plus 20.07 equals X. Add those together, we're going to get 63.55 AMU. Okay, and then there would be your answer right here. So I want y'all to quickly pause the video, work through the next problem, and then we are done with our notes. And I will show you the answers after you have, resumed the video. Okay, so hopefully y'all paused the video. So now let me show you the answer to this. All right, so here is your answer. First thing to note is that these did not add up to 100, so you did need to make sure to find your percent abundance. So we did 13 over 19, that gave us 68.42, 5 over 19, which gave us 26.32, and then 1 over 19, which gave us 5.263%. Okay, plug that into your isotopic abundance, so average atomic mass formula. So isotope times abundance plus isotope times abundance plus isotope times abundance. You should have ended up with 70.74. hopefully this y'all got this. Let us know if you've got any questions. Please reach out via email, or if you just want to ask us when we get back into class next class, please do that. So see y'all then.